Hi, welcome to Digital Electronics. Today I'm going to talk on Chapter 4, Function of Combinational Logic Circuit under the subtopic 4-bit parallel binary ripple carry adder circuit. So this is going to be under the Chapter 4.2. So in 4-bit parallel binary ripple carry adder, uh, so under the 4-bit full adder process 4 bits input A, which is A4, A3, A2, A1 with another 4-bit input B, B1, B2, B3 and B4 and 1-bit input C in to produce 4-bit sum, which is S1, S2, S3 and S4 and 1-bit carry C4 as output. So in general, you're going to have 3 input, which is the A. So you have A1, A2, A3, A4. Input B, which is B1, B2, B3, B4. And also input C in as input. And when you process all the input, you're going to have an output of two kind, which is 4-bit binary sum, S1, S2, S3, S4, and the carry C4. So how it looks under the circuit diagram. So you're going to have a C in. So when you have a C in, this is very important to start with 0 or earth grounded. So that's why you're going to have a 0 over here. And then you have A1, A2, B1. So it's going to process A1 plus B1 plus C in. Whatever output, you're going to have a sum over here as naught. And you're going to have a C in, C1 over here as an output. So the C1, which is the output of first full adder, will be going as the input of full adder number 2. Together with this, we're going to addition of A1, A2 and B2. Then the sum of this particular process will come out as S1. And also the carry will be C2. So this process continues until you got the MSB as a C sum 3 and C4. So this is an example. Let's say you have A which is 0101 and B1101 are applied for the 4-bit parallel adder. So you're going to analyze what is the resulting at the sum and see out. First, you need to take the input A and the input B over here. Second, always make sure you start with LSB. So the LSB over for A is the 1 and you need to put at the first full adder, A1. Same goes to the B. So the LSB over here is the 1 and you take it out to the B1 over here. And since we already know C in is equal to 0, so we can start to analyze this particular situation. So how you're going to do this is you need to start from right to left in this. So you have to start from the LSB to the MSB. For the LSB, you're going to have so you have already written all everything. So you have 0 1 0 1, so you have 4, so you have 0 1 0 1. You have 1 1 0 1, so you have 1 1 0 1. Now we're going to add in C in, which is the 0. So for the first sum, A0 plus B0 plus C in. So here is the 1, so you just put 1 over here. This is another 1, so here, and C in is 0. So 1 plus 1 plus 0, is going to have a sum of 1 and carry of 1. Sorry, sum as 0, the carry is 1. So that's why you write your sum 1 as 0 and you put your carry to here. So this carry is going in as the input for the second full adder. Right, now you already have 0. You have a 0 over here. So input A1 is 0, input B1 is 0, and C1 is 1. So 0 plus 0 plus 1, you're going to have a sum 1 and carry 0. So you write your sum 2 as 1 and take out your carry to here, become 0. And this, you're going to analyze the same for the third full adder. So the third full adder, A2 plus B2 plus C2. So A2 is 1, B2 is 1, and C2, you take it out from the carry from here, which is 0. So you just put over here 0. So 1 plus 1 plus 0 is sum is 0, carry is 1. So you write your sum as 3. Sum number third sum will be 0, and your carry going to be here. So for this one, A3 plus B3 plus C3. So over here is 0. My mistake. This is wrong. A3 is 0. B3 is 1. So just 0 plus 1. And then you have 1 over here. So you have here. So it doesn't change the circuit. So 0 plus 1 plus 1. You're going to have a sum of 0 carry as 1. So you have a sum 4 equals to 0. You put the carry over here. C out is 1. So let's check with the mathematics. So you have 0, 1, 0, 1. So 0, 1, 0, 1 and 1, 1, 0, 1, 1, 1, 0, 1. So 1 plus 1 is 0. You have a carry 1. 1 plus 0 plus 0 is 1. 1 plus 1 is 0 carry 1. So you have 1 over here. 1 plus 0 plus 1 is 0 carry 1. So you have 0, 1, 0, 0. So you have 0, 1, 0, 0. And the carry as 1. So you have a 1 over here. So this confirms that this particular addition will end up as the result of as mentioned earlier. So now we're going to go for the next step, which all this around we do the addition. How about we go for the subtraction? So this particular 4-bit full adder, you can do subtraction of a signed number by applying second complement method, which is inverting all the bits before adding 1. So we can recall our topics before. For the second complement, we always invert the bits and add 1. So for example, like this. So this is minuet minus subtract. You have the difference. But now we're going to change the minus to become a positive. But to change this one, we need to change the value over here to a second complement method. So how we're going to do this is first we need to change all the bits and then add 1. For the changing the bits to invert, you need to use NOR get. The problem is the NOR gets, you have to use each of the bits one particular NOR get, independent NOR get. So, but this method is good. This is achievable, but in terms of economical, it is not. So we need a simpler way to do this. How are we going to do this? Is by using a XOR gate. First, before you do the XOR gate, we need to understand how it works. So XOR gate, you have 0, 0 become 0, 0, 1 is 1, 1, 0 become 1, and 1, 1 is 0. So if you see over here, there is a change of input 0, 1, you become 1, and 1, 0 is become 1. All right. Now, what we're going to do is we're going to use the input A as a control bit and B as it is and C out as out. So whenever the input is 0, input A is 0, we're going to have the Cout behave as a input B. So if you see over here, whenever input A is 0, 0, 0, so you're going to behave, the Cout is behaving similar to B. So you see over here, it started with 0, it becomes 0. If started with 1, it becomes 1. But when we have the input A as 1, the Cout will behave as inverted as B input. So if you see 1, 1, so you can see the B is inverting itself. So let's say you have a B of 0, it becomes Cout will become 1. If you have a B of 1, it will become 0. So we're going to use this situation to perform the second complement operation. So how are we going to do this? So since we need the second complement, so and we also have XOR which behave in under the control bit A. If 1, it will be inverting. So we're going to use a slightly modified adder. So the adder is you're going to have a input over here. So don't worry about this. And you're going to have a B binary number, and we're going to have a control C in, and we have a sum and C out. Right. Technically the control bit over here is going to be here controlling, and B is controlling this particular control adder or subtractor. So A will behave like a B. Right, don't worry about that. Sorry, this is controlling this one, and this particular is nothing to do with this one. It's only controlling this and this. Okay, let's go for the next step. So for the example 2, obtain the sum and Cout when A is equals to 0, 1, 0, 1 is subtracted with B 0, 0, 0, 1. So 0, 1, 0, 1 is minusing 0, 0, 0, 1. So how are we going to do this? Let's put 0, 1, 0, 1. So you have an MSB on the left. So 0, 1, 0, 1 and B 0, 0, 0, 1. So you have 0, 0, 0, 1. And you need to select S1 over here. So because you want to have the capability of doing inverting on the B. So we wanted to invert this particular operation. So that's why we need to put 1 over here. So when you have 1, 0, 1, 0, 0, and then you have 1 over here. So 1 and 1. So you have 1 and 1, it becomes 0. So that's why you have a 0 over here. And then over the second one, 0, 1, you have a 0, 1. You're going to have 1. So that's why you have a 1 over here. 0, and because here 0 and 1, you're going to have 1. And 0, 1, you're going to have 1. This the third part. And then this is successfully inverted. If you see over here, this is 1, it becomes 0. 0 become 1, 0 become 1, and 0 become 1. So if you go over here, it will become 1, 1, 1, and 0. So because here is already C in is 1, so you're going to have, you need to perform step by step to do it. So now we're going to for the first step, that is analyzing the A1, B1, and also the C in. So you need to add 1 plus 0, 1 plus 0 plus 1. That will be coming out a sum of 0. Your sum will become 0 over here. So you repeat the same and your carry is also, your carry become 1. So next, you need to analyze step by step like I mentioned earlier in the earlier stage. You have to analyze one by one like this until you obtain your sum and also Cout. Let's check in the mathematical. So you have 0, 1, 0, 1. So you have 0, 1, 0, 1. You have 1, 1, 1, 0, 1, 1, 1, 0. And because your C in is 1, so you just need to put 1 over here, the green color, and you add up, and you're going to have 0 0 1 0. So you have 0 0 1 0, and your carry is 1. That's how you do the subtraction, and then you got to get the result. Right, this is a example how you can do 4-bit parallel binary using 8-bit adder. So if you have you need to do 8 bits, because all the time we are only analyzing bit 1, bit 2, bit 3, bit 4. But here you can use this method to do 8 bits. So you need to use 2 unit of IC 741 LS283 by cascading the pin number 9 and 7. So pin number 9, the output of C4, you need to cascade with the input of C in, which is pin number 7 over here. So this is how you have the inputs over here. So this is the first 4 bits input of A, the second 4 bits of input of A. Here B1, B2, B3, 4, B5, B6, B7, 8. And please make sure your C in of pin number 7, the first IC, is grounded. Okay, and also you have your VCC power, and the pin number 8 is grounded. So when you total up the input A and input B, you're going to have a sum over here, and you are going to have a sum over here. So don't forget to get the sum number 1, 2, 3, 4, 5, 6, 7, 8, and C out as a carry output. Continue to document 4.3 for the look ahead carry adder circuit. Thank you.